1. Basic, von Neumann, Architecture of Computers. Instruction Format, Instruction Set. Operation Principle of Modern Computers. OS and Hardware, Processor, Registers, Interrupts and its Management, I/O Operations, Memory Structure and Hierarchy, DMA. Von Neumann Architecture. The von Neumann architecture is a design model for a stored program digital computer. Its main characteristic is a single separate storage structure, the memory, that holds both program and data. Sequential processing machine. CPU in modern computers combines the control unit and ALU, memory. O can hold both data and program processing. That data. O RAM in modern computers, control unit. O manages the process of moving data and program in and out of the memory. O deals with executing program instructions one at a time. O has a register to hold intermediate values, input/output. O allows the interaction with the computer. ALU, arithmetic logic unit. O calculations upon the data. O plus comma dash comma times comma divided by equals. O accumulator. Register that holds intermediate values, bus. O a set of wires that collects the information. The arrows between components. O information flows here. O is shared between the program memory and data memory. Equals von Neumann bottleneck. Features of von Neumann computer. O both instructions, code, and data, variables and input/output, are stored in memory. O memory is an collection of binary digits, bits, that have been organized into bytes, words, and regions with addresses. O the code instructions and all data have memory addresses. O each instruction has to be moved to the registers to be executed. O only the registers have the smarts to do anything with the instructions. Memory can't. O to save a result computed in the registers, it has to be moved back to memory. OS and compilers keep the instructions and data in memory organized so it doesn't get mixed up together. Operation Principle of Modern Computers. OSJE základní program, který se spustí automaticky po zapnutí počítače, který jde činnost jeho technických prostředků podle požadavku uživateli. Ukulele OS, o jde asynchronizovat procedure podlovit zdroj. O poskytovat služby programátorům uživatelům. Vytváří virtuální prostředky. O poskytují procesem systému vůdech. Instruction set, command set, the basic set of commands, or instructions, that a microprocessor understands. Size of the instruction set differentiates between RISC, small sets, and CISC, large sets. Microprocessors, is the part of the computer architecture related to programming, including the native data types. Instruction format equals what does each bit mean? Format strojov instructs obsahuj, o operatní kod. Jaka instructs se bud vykonovat o adresa výstupního operandu, identifikuj operand, y, se který bud instructs prokovat o adresa výstupního operandu, stanoví adresu, y, na kterou bud popravdany instructs ulazan vysledik o adresa nasledn vykonane instructs, Jaka instructs I moprosator vykonat nasledovn registers. Discrete memory location within the CPU designed to hold temporary data and instructions, addressed by mechanisms other than main memory and can be accessed more quickly. Modern CPU will hold a number of registers. There are a number of general-purpose registers that can be used to hold intermediate results whilst working through a calculation or algorithm. Normally at the top of the memory hierarchy, and provide the fastest way to access data, registers are normally measured by the number of bits they can hold, for example, an 8-bit register or a 32-bit register. A processor often contains several kinds of registers, that can be classified accordingly to their content or instructions that operate on them. Program counter, holds the address in memory of the next instruction. Instruction register, holds the current instruction to be executed, having been fetched from memory. MBR, buffer is a commonly used computer term to describe memory designed to hold data that is on its way to somewhere else. Processor central processing unit, core of every personal computer, carries out the instructions of a computer program by performing the basic arithmetical, logical, and input/output operations of the system. the speed of the CPU is measured in Hertz and refers to the number of cycles per second that the CPU runs at. Two parts of CPU are the arithmetic logic unit, ALU, which performs arithmetic and logical operations, and the control unit, CU, which extracts instructions from memory and decodes and executes them, calling on the ALU when necessary. From large vacuum tubes and electrical relays to small transistor processors, the fundamental operation of most CPUs is to execute a sequence of stored instructions called a program. Interrupts and its management. It is a signal to the processor emitted by hardware or software indicating an event that needs immediate attention, a method for asynchronous event handling where the processor interrupts execution of a sequence of instructions, handles the interrupt, and then resumes previous activity. If an interrupt is signaled to the processor, if interrupt handling is enabled, the machine instruction currently being processed is completed first. Then the address of the next machine instruction that should be processed if the interrupt did not occur is stored on the stack. Then, according to the interrupt table, the interrupt handler is called to service the event that raised the interrupt. The interrupt handler is responsible for returning the state of the processor to the same state as it was at the beginning of the interrupt at its end so that the computation of the interrupted task is not affected. At the end of the interrupt handler is a return, RET, instruction that fetches the return address from the stack and thus causes the next machine instruction to be fetched from that address. The interrupted task thus does not recognize that the interruption service has taken place until a delay. Internal interrupts. Internal interrupts are caused by the processor itself, which signals problems in the processing of machine instructions and allows the operating system to react to these events in the most appropriate way. This is, for example, an attempt to divide by zero, a violation of memory protection, the absence of a math coprocessor, a page crash, etc. External interrupt. An external interrupt, also a hardware interrupt, is referred to as coming from an I/O device, i.e., from the processor's point of view, they come from the outside. The input-output device thus has the possibility to asynchronously request the attention of the processor and thus ensure its service at the moment when it needs it, regardless of the currently processed task. External interrupts are delivered to the processor through the interrupt controller, which is a specialized circuit that allows the priority of individual interrupts, their distribution among different processors, and other related actions. I/O operations. I/O operations on a computer can be extremely slow compared to the processing of data. I/O device can incorporate mechanical devices that must physically move, such as a hard drive seeking a track to read or write. A simple approach to I/O would be to start the access and then wait for it to complete. Blocks. The progress of a program equals very slow. When a program makes many I/O operations, the processor can spend most of its time waiting for I/O operations to complete. Solution. It is possible to start the communication and then perform processing that does not require that the I/O is completed equals asynchronous I/O. Asynchronous I/O is used to improve throughput, latency, and or responsiveness. DMA, direct memory access, a technique for transferring data from memory to a device without passing it through the CPU. Computers with DMA channels can transfer data to and from devices faster. DMA can save processing time and is a more efficient way to move data from the computer's memory to other devices. NAP. A sound card may need to access data stored in the computer's memory, but since it can process the data itself, it may use DMA to bypass the CPU. Memory structure and hierarchy. A memory hierarchy in computer storage distinguishes each level in the hierarchy by response time. Goals while creating a memory have lots of it, gigabytes, terabytes, etc., enough to contain the entire address space. Make it fast as CPU registers. Make it affordable, not too expensive. The closer to the CPU a level in the memory hierarchy is located, the faster, smaller, and more expensive it is. Registers allow to store 32 words, which can be accessed extremely fast. Cache is located close to the CPU and composed of a relatively small amount of fast and expensive memory. SRAM, main memory is significantly larger and composed of slower and cheaper DRAM. hard drive contains all information that is stored in the machine. Offers a vast amount of storage space, cheap but slow. There are 4 major storage levels, 1 internal processor registers and cache. 2 main the system RAM and controller cards. 3 online mass storage secondary storage. 4 offline bulk storage tertiary and offline storage. 2 computational model and operating systems, batch processing, host/terminal, cloud computing. Computational model in computability theory and computational complexity theory. A model of computation is the definition of the set of allowable operations used in computation and their respective costs. It is used for measuring the complexity of an algorithm in execution time and/or memory space. By assuming a certain model of computation, it is possible to analyze the computational resources required or to discuss the limitations of algorithms or computers. Used for measuring the complexity of an algorithm in execution time and/or memory space. Some examples of models include, O Turing machines, O lambda calculus, O finite state machines, O combinatory logic, O recursive functions, O production systems. Operating system equals the software that supports a computer's basic functions, such as scheduling tasks, executing applications, and controlling peripherals. Equals a collection of software that manages computer hardware resources and provides common services for computer programs. Operating system is defined by a virtual machine that supports a particular conceptual model of computation. O part of that model is a set of resources that will be used in computations. O programmers need to understand that model in order to develop apps for that OS. O process, fundamental unit of computation. O file, fundamental unit of information storage, for hardware. Functions such as input and output and memory allocation. The operating system acts as an intermediary between programs and the computer hardware, although the application code is usually executed directly by the hardware and will frequently make a system call to an OS function or be interrupted by it. Time-sharing operating systems schedule tasks for efficient use of the system and may also include accounting for cost allocation of processor time, mass storage, printing, and other resources. Batch processing. Batch processing is execution of a series of programs, jobs, on a computer without manual intervention. The term originated in the days when users entered programs on punch cards. They would give a batch of these programmed cards to the system operator, who would feed them into the computer. All input data are pre-selected through scripts, command line parameters, or job control language. An example of batch processing, the way that credit card companies process billing. The customer does not receive a bill for each separate credit card purchase but one monthly bill for all of that month's purchases. The bill is created through batch processing, where all of the data are collected and held until the bill is processed as a batch at the end of the billing cycle. Plus can shift the time of job processing to when the computer is not busy and avoids idling with manual intervention and keeps high rate of utilization and different priorities for batch and interactive work and used in database updates. Opposite of batch processing, transaction processing or interactive processing. In interactive processing, the application responds to commands as soon as you enter them. Client-server architecture. O client machine accessing data and programs on a server machine. Host-to-terminal architecture. O terminal device providing a screen and keyboard to a host machine. X Windows Terminal Protocol, a unique blend, peer-to-peer architecture. O two similar machines operating in harmony as peers on the network. 1. Client-server architecture. Client/server equals commands and replies exchanged. Client is the fact that it is running an application program. The program could be a word processor, database, or some custom application. The client is doing real processing work. For example, the word processor is reformatting a paragraph or checking spelling. The database is comparing a zip code to the zip codes in each of several thousand customer name records to select everyone in zip code 94301. The client is doing real processing work. The server is providing resources to the client. The most common resource to provide is simple disk service. The client is accessing data that is physically present on a remote file server. The service that is provided is the management of the disk drive, including the disk directory, file allocation table, and file read/write capabilities. In our database example, the client reads a single customer record from the server and compares zip codes in the record. It then continues, reading one record at a time from the server. The server serves, the client processes. 2. Host-to-terminal architecture. Terminal/host equals character-oriented information exchanged in a terminal/host relationship. The processing work is occurring on the host and the video display is managed by the terminal. The terminal device doesn't do any application processing, it simply displays the screen from the host and accepts keystrokes from the user to be sent to the application that is running on the host machine. The predominant information exchanged between communicators in a terminal/host conversation is character-oriented. Processing is done on the host, characters are input from and displayed at the terminal. 3. Peer-to-peer architecture. When two machines are communicating as equal partners, we say they are in a peer-to-peer relationship. A true peer-to-peer relationship is hard to find. A true peer-to-peer relationship implies two processes, programs, that are exchanging data equally. For example, consider a pair of database programs that are working together to sort a large database. One program sorting half the data while the other program is sorting the other half. Cloud computing, it is the use of computing resources, HW and SW, which are available in a remote location and accessible over a network, typically the Internet. Users are able to buy these computing resources, storage and computing power, as a utility, on demand. Cloud computing entrusts remote services with a user's data, software, and computation. The cloud also focuses on maximizing the effectiveness of the shared resources. Cloud resources are usually not only shared by multiple users but as well as dynamically reallocated as per demand. This can work for allocating resources to users in different time zones. The term moving cloud also refers to an organization moving away from a traditional CAPEX model, buy the dedicated hardware and depreciate it over a period of time, to the OPEX model, use a shared cloud infrastructure and pay as you use it. Hardware and software demands on the user's side decrease. The only thing the user's computer needs to be able to run is the cloud computing system's interface software, which can be as simple as a web browser, and the cloud's network takes care of the rest. Front end of the system, O user's computer, O application required to access the cloud system. Back end of the system equals the cloud, O various computers, servers, and data storage systems. O usually, each application will have its own dedicated server. O central server administers the system, monitoring traffic and client demands, follows a set of rules called protocols, and uses a special kind of software called middleware. Middleware allows networked computers to communicate with each other. O most of the time, servers don't run at full capacity. Unused processing power waste. Divide physical server into smaller virtual servers with independent equals server. Virtualization reduces the need for more physical machines. Storing data, at least double of the required storage capacity to make backup copies. O redundancy problems of cloud computing, security and privacy. O companies can't keep their company's information under lock and key. O companies offering cloud computing services live and die by their reputation. O access, authentication techniques such as usernames and passwords each use 3 OS services and generic OS components, processes, memory management, I/O system, administration of external memory, files, networking, security, command interpreter, GUI. Major operating systems include MS Windows, Sun Solaris, Mac OS, and Unix/Linux family. The kernel, O central component of most OS. O manages the system's resources. O communication between HW and SW. O provides the lowest level abstraction layer for the resources, memory, processors, and I/O devices, that application software must control to perform its function. It typically makes these facilities available to application processes through inter-process communication mechanisms and system calls. Basic functions that an OS should provide: O CPU and process management, O memory management, O I/O management, O information and storage management, O network management. Basic services: O user interface, O program execution, O security, O device management, O resource allocation and accounting processes, CPU and process management. Every program running on a computer is a process, only one process per CPU can be run at a time. Von Neumann, O bypassing this by multitasking capabilities. Since the early 1960s, modern operating systems enable concurrent execution of many processes at once via multitasking even with one CPU. Process management is an OS's way of dealing with running multiple processes. Since most computers contain one processor with one core, multitasking is done by simply switching processes quickly. In many systems there is a background process, such as the system idle process in Windows, which will run when no other process is waiting for the CPU. Memory management. Current OS, memory is arranged in a hierarchical manner. 1. Fastest registers. 2. CPU cache. 3. RAM. 4. HDD/SDD, virtual memory management. OS coordinates the use of these various types of memory by tracking which one is available, which is to be allocated or deallocated, and how to move data between them. O increases the amount of memory available for each process by making the disk storage seem like main memory. O speed penalty associated with using disks or other slower storage as memory. Managing virtual addresses. If multiple processes are in memory at once, they must be prevented from interfering with each other's memory. O separate address spaces. Virtual address space, typically from address 0 up to the maximum size of virtual memory, as uniquely assigned to it. I/O management, system. OS allocates requests from applications to perform I/O to an appropriate device and provides convenient methods for using the device. O the application does not need to know implementation details of the device. Peripherals are controlled by the kernel through device drivers. O device driver is a program or routine developed for an I/O device. O device driver implements I/O operations or behaviors on a specific class of devices. O for example, to show the user something on the screen, an application would make a request to the kernel, which would forward the request to its display driver, which is then responsible for actually plotting the character/pixel. Kernel is responsible for the following actions regarding I/O: O scheduling, O spooling and device reservation, O buffering, O error handling, O caching. Administration of external memory. CPU can only directly access data that is in main memory. To process data that resides in external memory, the CPU must first transfer it to main memory. Accessing external memory to find the appropriate data is slow, milliseconds, in relation to CPU speeds. External memory, secondary memory, allows the permanent storage of large quantities of data. Files and OS. Modern file systems comprise a hierarchy of directories. File is a collection of data. File system are organized. Files equals how the system makes the data available. OS manages the files and the FS. How can a file be named? NTFS, FAT, FAT32, mountable system. Through commands. Unix programs need to read and write files and directories, create and delete them, search them, list file information. Permission management. Networking. Although not a core part of the operating system, the network manager has become essential in modern-day computing. Most current operating systems are capable of using the TCP/IP networking protocols. This means that one system can appear on a network of the other and share resources such as files, printers, and scanners using either wired or wireless connections. Telnet, a network protocol that allows a user on one computer to log on to another computer that is part of the same network. Many operating systems also support one or more vendor-specific legacy networking protocols as well, for example, SNA on IBM systems, DECnet on systems from Digital Equipment Corporation, and Microsoft-specific protocols on Windows. Specific protocols for specific tasks may also be supported, such as NFS for file access. Network Manager is essential in modern-day computing. Current operating systems are capable of using the TCP/IP networking protocols. One system can appear on a network of the other and share resources such as files, printers, and scanners using either wired or wireless connections. TCP/IP, Transmission Control Protocol/Internet Protocol, is the basic communication language or protocol of the Internet. It can also be used as a communications protocol in a private network. Many OS support one or more vendor-specific networking protocols such as SNA on IBM System Security, 2 levels, internal, protecting the computer's resources from the programs concurrently running on the system. External, file sharing, print services, email, websites, and file transfer protocols, FTP. Dealt with using add-on software like firewalls and antivirus programs. Security and networking. The network allows transmission of data from the clients to the server. There are several points on the network where a hacker could eavesdrop or steal important packets of information. These packets may contain important confidential data such as passwords or company details. It is important that these networks are secured properly to keep unauthorized professionals away from all the data stored on the server. This can be done by encrypting important data being sent on the network. Command interpreter, the part of OS that interprets commands entered by human or a program and carries them out. In other words, a command interpreter is a program which reads the instructions given by the user. It then translates these instructions into the context of the operating system followed by the execution. Command interpreter is also known as Shell Graphical User Interface, GUI. All operating systems need to provide an interface to communicate with the user. This could be a command line interface or a graphical user interface. A graphical user interface, GUI, is a type of user interface which allows people to interact with a computer and computer-controlled devices which employ graphical icons, visual indicators, or special graphical elements. A command line interface or CLI is a method of interacting with an operating system or software using a command line interpreter. This command line interpreter may be a text terminal, terminal emulator, or remote shell client. The concept offered results on demand, compared to batch-oriented mechanical punch card input technology. 3 systems and application on the World Wide Web platform. Principles, functions, management. Markup, scripting, and programming languages, client-side/server-side technologies. Principles of systems and applications on the World Wide Web platform. Systems and applications on the World Wide Web platform are built on a set of principles that guide their design and development. These principles include open standards, ensuring that different systems and applications can work together seamlessly by using common standards and protocols. Interoperability, ensuring that systems and applications can exchange information and work together without restriction. Scalability, ensuring that systems and applications can handle large amounts of data and traffic. Functions of systems and applications on the World Wide Web platform. Systems and applications on the World Wide Web platform provide a range of functions, including browsing, allowing users to access and navigate through web pages and websites. Searching, enabling users to search for specific information and content. Communicating, providing tools for communication such as email, messaging, and social media. Managing information, organizing and storing data in a way that is easily accessible and searchable, as well as providing tools for analyzing and manipulating that data. Markup, scripting, and programming languages. Developers use a range of technologies and languages to create systems and applications on the World Wide Web platform, including markup languages, such as HTML and XML, which are used to structure and format web pages and content. Scripting languages, such as JavaScript and Python, which are used to create interactive features and behavior on web pages. Programming languages, such as Java and C#, which are used to create server-side applications. Client-side and server-side technology. Systems and applications on the World Wide Web platform use both client-side and server-side technologies to provide functionality. Client-side technologies, such as HTML, CSS, and JavaScript, which run in a user's web browser and provide interactive features such as forms, animations, and media playback. Server-side technologies, such as Java, Python, or PHP, which run on a web server and provide features such as database integration, authentication and security, and content management. Management and deployment. Managing and deploying systems and applications on the World Wide Web platform requires a range of tools and techniques, including version control systems, such as Git, which are used to manage changes to code and collaborate with other developers. Software testing frameworks, such as Selenium, which are used to test the functionality and performance of web applications. Deployment automation tools, such as Jenkins, which automate the process of deploying code to servers. Hosting and infrastructure management solutions, such as cloud platforms and web hosting providers, which provide the infrastructure required to run web applications. For OS architecture and principles of the OS, hierarchical layered architecture, microkernel, modular architecture, virtual machines. OS principles. The operating system is the SW layer between user applications and the HW kernel, core of an operating system, SW responsible for running programs and providing secure access to the machine's HW, many programs and limited resources equals kernel decides when and how long a program should run equals scheduling. Accessing the HW directly is very complex, many different HW designs. Kernel relies upon software drivers that translate the generic command into instructions specific to that device. OS kernel is not strictly needed to run a computer. Programs can be directly loaded and executed on the bare metal machine, complicated for programmers. Newer systems use kernels and OS. The Windows NT branch of Windows has a hybrid kernel. It's neither a monolithic kernel where all services run in kernel mode or a microkernel where everything runs in user space. This provides a balance between the protection gained from a microkernel and the performance that can be seen in a monolithic kernel, as there are fewer user/kernel mode context switches. Layered architecture. The operating system is divided into a number of layers, levels, each built on top of lower layers. The bottom layer, layer 0, is the hardware. The highest, layer N, is the user interface. With modularity, layers are selected such that each uses functions, operations, and services of only lower-level layers. E.g. Unix. In this, all layers are part of the kernel, and each layer can talk to only a few other layers. Application programs and utilities live above the kernel. Microkernel. Microkernel is the near minimum amount of SW that can provide the mechanisms needed to implement OS. The major microkernel operating system is Mach, implements minimal OS services such as thread management, address spaces, and inter-process communication. All other services, those normally provided by the kernel such as networking, are implemented in user space programs referred to as servers. In theory, the system is also more stable, because a failing server simply stops a single program, rather than causing the kernel itself to crash. Modular design. A modular kernel is an attempt to merge the good points of kernel-level drivers and third-party drivers. In a modular kernel, some part of the system core will be located in independent files called modules that can be added to the system at runtime. You can replace or add any one component, module, without affecting the rest of the system. Many operating systems implement kernel modules, e.g. Linux. Each core component is separate, loadable on demand. Modules are somehow a hybrid between the layered and microkernel approach, clean software engineering approach, but modules are inside the kernel space. They don't require the overhead of message passing or compromise with performance benefits. Virtual machines is a software implemented abstraction of the underlying hardware, which is presented to the application layer of the system. Virtual machines may be based on specifications of a hypothetical computer or emulate the computer architecture and functions of a real-world computer, an efficient, isolated duplicate of a real machine. 5. Role of the operating system in current computers. Basic types, categorization, of operating systems and principles of their activities. Multitasking, cooperative, preemptive, multithreading. Comparison of MS Windows and Unix operating systems. OSJE Zakladny program, Sectari se spasti automatiki posapnoti posita sectari edi sinos jaho technikic prostit podal posadovku ozavitelli. Ukali os, edit asynchronizovat prosadia pidlovat jims droj. Poskitovat sluzby programator maozavitelm. Vitve itzv. Virtual ni prostidki. Poskitui processum system uvutage. Druhi os, podal poktuozavatel jednozavatelsk visozavatelsk podal poktuprose, der moha probihat saukas jedna processovi multitasking podal interactive nosti batch processing, programi naktini du vstupni fronti ulo apak postupnsperkovani, visledki bili ulazani du vstupni fronti interactive, Sprkovani program ediozavatel interactive z terminal multithreading, the ability of OS to execute different parts of a program, called threads, simultaneously. Multithreading is the ability of a program or an OS process to manage its use by more than one user at a time and to even manage multiple requests by the same user without having to have multiple copies of the programming running in the computer. Multitasking, the ability of an operating system to run, at least ostensibly, several processes at the same time. The OS kernel very quickly alternates the processes running on the processor, so that the computer user has the impression that they are running at the same time. You can switch to another task without ending the task in progress. Enables activities to run in parallel, network management. Programs can work together in ways other than passing entire sets of data. Better use of the machine's capabilities. It is a must for multi-user operation. Higher overhead time consumption. More complex and therefore more expensive, with higher demands on resources. Little safety and higher failure rate if not well designed, deadlock. Preemptive versus cooperative. In preemptive multitasking, the OS decides which application should receive the processor's attention. In contrast to cooperative multitasking, in which a busy application could monopolize the computer for as much as several minutes, a computer with a preemptive multitasking system seems much more responsive to user commands. Cooperative, it requires active participation in running tasks. Each task is obliged to pass control back to the operating system with a system call often enough, which can then start another task, which after a while voluntarily gives up the processor again, etc. and easier implementation of the operating system. An incorrectly programmed task that does not return control back to the OS will cause the system to halt. Preemptive. In preemptive multitasking, the operating system fully decides on the allocation and removal of the processor to individual tasks. At regular intervals, roughly 100x to 1000x per second, it interrupts the execution of the running program, evaluates the current situation, which tasks are requesting processor allocation, their priority, etc., and lets either the task get interrupted or another task that is interested in running again processor allocation. However, even in preemptive multitasking, a task can voluntarily request a context switch and give up the rest of its quantum. Plus, the computer does not freeze. More complex OS implementation and the need for hardware support in the computer's processor, privileged mode. Unix operating system, relatively easy, compared to Multix, which tried to deal with everything and apply advanced ideas, multitasking, multi-user, hierarchical file system, FS tree with one root, almost everything is a file, data, configuration files, are stored as a plain text. The emphasis is on relations between programs rather than on the programs itself. Prace, a set of one-purpose tools, which do their task perfectly, connecting tools into each other. Output of one program is redirected into the input of another one. Use of complete programs in other programs. Text processing-oriented Unix is composed of the OS core, system tools, utility, and other applications. Its monolithic core is taking care of low-level events, kernel space, and the programs run in user space. Programs communicate with the core using the system calls, daemons, which makes a stable API for programs. Windows vs Unix. As far as operating systems go, to some it would seem as if Unix has a clear advantage over Windows. Unix offers greater flexibility than Windows operating systems. Furthermore, it is more stable and it does not crash as much as Windows. To some, Unix is just as easy to use as Windows, offering a GUI interface as well as command line. But there are users out there that believe Unix is for computer gurus only, claiming that the fragmentation of the Unix GUI is its greatest competitive weakness. Another main difference between Unix and Windows is the process hierarchy which Unix possesses. When a new process is created by a Unix application, it becomes a child of the process that created it. This hierarchy is very important, so there are system calls for influencing child processes. Windows processes on the other hand do not share a hierarchical relationship. Receiving the process handle and ID of the process it created, the creating process of a Windows system can maintain or simulate a hierarchical relationship if it is needed. The Windows operating system ordinarily treats all processes as belonging to the same generation. In summary, the best way to choose between Unix and Windows is to determine organizational needs. If an organization uses mostly Microsoft products, such as Access, FrontPage, or VB Scripts, it's probably better to stick with Windows. But, if reliability, universal compatibility, and stability are a concern, Unix would probably be the way to go. 6 Operating Systems: Mac OS, Linux. Categorization: Operating systems for mobile devices, iOS, Android, Symbian. Other systems, firmware, BIOS, UEFI. Mac OS is a series of graphical user interface-based operating systems developed by Apple Incorporated for their Macintosh line of computer systems. The original version was the integral and unnamed system software first introduced in 1984 with the original Macintosh, and referred to simply as the system software. This is credited with popularizing the graphical user interface concept. Mac OS releases have existed in 2 series, Classic Mac OS from 1984 to 2000 and Mac OS X from 2001 to present. Both series share a general interface design, but have very different internal architectures. Linux is a Unix-like computer operating system assembled under the model of free and open-source software development and distribution. The defining component of Linux is the Linux kernel 11, an operating system kernel first released October 5, 1991 by Linus Torvalds. Since the C compiler that builds Linux and the main supporting user space system tools and libraries originated in the GNU project, initiated in 1983 by Richard Stallman, the Free Software Foundation prefers the name GNU/Linux. Linux was originally developed as a free operating system for Intel x86-based personal computers. It has since been ported to more computer hardware platforms than any other operating system. It is a leading operating system on servers and other big iron systems such as mainframe computers and supercomputers. More than 90% of today's 500 fastest supercomputers run some variant of Linux, including the 10 fastest. Linux also runs on embedded systems, devices where the operating system is typically built into the firmware and highly tailored to the system, such as mobile phones, tablet computers, network routers, building automation controls, televisions, and video game consoles. The Android system in wide use on mobile devices is built on the Linux kernel. iOS, previously iPhone OS, is a mobile operating system developed and distributed by Apple Incorporated, originally released in 2007 for the iPhone and iPod Touch platforms. It has been extended to support other Apple devices such as the iPad and Apple TV. Unlike Microsoft's Windows Phone and Google's Android, Apple does not license iOS for installation on non-Apple hardware. As of September 12, 2012, Apple's App Store contained more than 700,000 iOS applications, which have collectively been downloaded more than 50 billion times. It had a 21% share of the smartphone mobile operating system units shipped in the fourth quarter of 2012, behind only Google's Android. In June 2012, it accounted for 65% of mobile web data consumption, including use on both the iPod Touch and the iPad. At the half of 2012, there were 410 million devices activated. According to the special media event held by Apple on September 12, 2012, 400 million devices have been sold through June 2012. Android is a Linux-based operating system designed primarily for touchscreen mobile devices such as smartphones and tablet computers. Initially developed by Android, Inc., which Google backed financially and later bought in 2005, Android was unveiled in 2007 along with the founding of the Open Handset Alliance, a consortium of hardware, software, and telecommunication companies devoted to advancing open standards for mobile devices. The first Android-powered phone was sold in October 2008. Android is open source and Google releases the code under the Apache license. This open source code and permissive licensing allows the software to be freely modified and distributed by device manufacturers, wireless carriers, and enthusiast developers. Additionally, Android has a large community of developers writing applications, apps, that extend the functionality of devices, written primarily in a customized version of the Java programming language. In October 2012, there were approximately 700,000 apps available for Android, and the estimated number of applications downloaded from Google Play, Android's primary app store, was 25 billion. Symbian is a mobile operating system, OS, and computing platform designed for smartphones and currently maintained by Accenture. Symbian was originally developed by Symbian Limited, as a descendant of Psion's ePOC and runs exclusively on ARM processors, although an unreleased x86 port existed. The current form of Symbian is an open-source platform developed by Symbian Foundation in 2009, as the successor of the original Symbian OS. Symbian was used by many major mobile phone brands, like Samsung, Motorola, Sony Ericsson, and above all by Nokia. It was the most popular smartphone OS on a worldwide average until the end of 2010, when it was overtaken by Android. Firmware. In electronic systems and computing, firmware is the combination of persistent memory and program code and data stored in it. Typical examples of devices containing firmware are embedded systems, such as traffic lights, consumer appliances, and digital watches, computers, computer peripherals, mobile phones, and digital cameras. The firmware contained in these devices provides the control program for the device. Firmware is held in non-volatile memory devices such as ROM, EPROM, or flash memory. Changing the firmware of a device may rarely or never be done during its economic lifetime. Some firmware memory devices are permanently installed and cannot be changed after manufacture. Common reasons for updating firmware include fixing bugs or adding features to the device. This may require physically changing ROM integrated circuits, or reprogramming flash memory with a special procedure. Firmware such as the ROM BIOS of a personal computer may contain only elementary basic functions of a device and may only provide services to higher-level software. Firmware such as the program of an embedded system may be the only program that will run on the system and provide all of its functions. BIOS. In IBM PC-compatible computers, the Basic Input/Output System, BIOS, also known as the System BIOS or ROM BIOS, is a de facto standard defining a firmware interface. The name originated from the Basic Input/Output System used in the CP/M operating system, released in 1976. The BIOS software is built into the PC, and is the first software run by a PC when powered on. The fundamental purposes of the BIOS are to initialize and test the system hardware components, and to load an operating system or other programs from a mass memory device. The BIOS provides a consistent way for application programs and operating systems to interact with the keyboard, display, and other input/output devices. Variations in the system hardware are hidden by the BIOS from programs that use BIOS services instead of directly accessing the hardware. The Unified Extensible Firmware Interface, UEFI, is a specification that defines a software interface between an operating system and platform firmware. UEFI is meant to replace the basic input/output system, BIOS, firmware interface, present in all IBM PC-compatible personal computers. In practice, most UEFI images provide legacy support for BIOS services. UEFI can support remote diagnostics and repair of computers, even without another operating system. The original EFI, Extensible Firmware Interface, specification was developed by Intel. Some of its practices and data formats mirror ones from Windows. In 2005, UEFI deprecated EFI 1.10, final release of EFI. The UEFI specification is managed by the Unified EFI Forum. 8 operating systems and SW for single-purpose, special, and smart devices, Smart Home, Smart Car, Smart Health, Smart Wearables. Why we have them? Single-purpose, special, and smart devices require specialized OS and software to cater to their specific functionalities. General-purpose OS and software, such as Windows or Mac OS, are designed to work on a wide range of devices with varying hardware configurations, making them less efficient and less secure for single-purpose devices. Specialized OS and software provide better performance, reliability, and security for these devices. Why are they better to their purposes? Specialized OS and software are better for their purposes because they are designed to be lightweight and efficient, which means they consume less power, require less storage space, and offer faster boot times. They are also optimized for specific hardware configurations, making them more reliable and less prone to errors. Additionally, specialized OS and software offer unique features and functionalities that are tailored to the needs of the specific device. What are the types? There are several types of specialized OS and software for single-purpose, special, and smart devices, including embedded OS. These are lightweight operating systems designed to run on devices with limited resources, such as microcontrollers and embedded systems. Examples include FreeRTOS, ThreadX, and VxWorks. Real-time OS, these are operating systems designed for devices that require precise timing and low latency processing, such as industrial control systems and medical equipment. Examples include QNX, Lynx OS, and ECOS. Mobile OS, these are operating systems designed for mobile devices such as smartphones and tablets. Examples include Android, iOS, and Windows Mobile. Wearable OS, these are operating systems designed for smartwatches and other wearable devices. Examples include watchOS, Tizen, and Wear OS. Smart Home OS, these are operating systems designed for home automation devices such as smart thermostats, smart locks, and smart lights. Examples include HomeKit, SmartThings, and Alexa. Smart Car OS, these are operating systems designed for automotive infotainment systems, GPS navigation, and other smart car features. Examples include Android Auto, Apple CarPlay, and QNX. How their OS operates. The operation of specialized OS depends on the type of device and its purpose. However, generally, specialized OS and software are designed to be lightweight, fast, and efficient. They have a smaller footprint, require fewer resources, and offer faster boot times than general-purpose OS. They also have specialized features and functionalities that cater to the specific needs of the device. For example, a smart home OS might have features such as voice recognition, remote access, and automation tools, while a wearable OS might have features such as heart rate monitoring and fitness tracking. In conclusion, specialized OS and software for single-purpose, special, and smart devices offer unique advantages in terms of performance, reliability, and security. They are designed to be lightweight, efficient, and optimized for specific hardware configurations. There are several types of specialized OS and software available, each with its own features and functionalities tailored to the specific needs of the device. 9 File systems, user management, user roles, process management, command interpreters in OS. File systems. A file system is a method used by operating systems to store, organize, and access files on a storage device. File systems are responsible for managing how data is stored, accessed, and retrieved from a storage medium, such as a hard drive or a flash drive. Different file systems have different characteristics, such as how they handle file permissions, how they organize files on a storage medium, and how they handle file names. User management. User management is the process of creating, deleting, modifying, and managing user accounts on an operating system. User accounts are used to authenticate users and grant access to resources on the system. User management is important for security purposes, as it allows administrators to control who has access to what resources on the system. User roles. User roles are a way of grouping users together based on their permissions and responsibilities. User roles can be used to manage access to resources on a system, by granting specific permissions to each role. For example, a system administrator might create roles for regular users, managers, and administrators, each with different levels of access to the system. Process management. Process management is the process of monitoring, controlling, and scheduling processes running on an operating system. A process is a program or application that is currently executing on the system. Process management is responsible for allocating resources to processes, such as CPU time and memory, and for terminating processes when they have completed their task. Command interpreters. Command interpreters are programs that allow users to interact with an operating system through a command line interface. A command interpreter interprets commands entered by the user and executes them on the system. Examples of command interpreters include the Windows command prompt, the Unix shell, and the Mac OS X terminal. Command interpreters are powerful tools that allow users to perform complex tasks on the system through simple commands. 10 network nodes, network types, and their implementation, network topologies. Network nodes. In computer networking, a node refers to any device that can communicate over a network. This includes computers, servers, routers, switches, and any other device that can send and receive data over a network. Nodes can be connected in various ways, depending on the network topology. Network types. There are several types of networks, including 1. LAN, Local Area Network. A LAN is a network that is confined to a small geographic area, such as a home, office, or school. LANs are typically used for sharing resources like printers, files, and internet connections. 2. WAN, Wide Area Network. A WAN is a network that covers a larger geographic area, such as a city, country, or even the world. WANs are used for connecting different LANs together. 3. MAN, Metropolitan Area Network. A MAN is a network that covers a larger geographic area than a LAN but smaller than a WAN. MANs are typically used to connect different LANs in a city or metropolitan area. 4. WLAN, Wireless Local Area Network. A WLAN is a type of LAN that uses wireless technology to connect devices to the network. Network topologies. A network topology refers to the physical layout of the network. There are several different network topologies, including 1. Bus topology. In a bus topology, all devices are connected to a single cable. Data travels along the cable and is received by all devices connected to it. 2. Ring topology. In a ring topology, devices are connected in a circular fashion, with data traveling in one direction around the ring. 3. Star topology. In a star topology, all devices are connected to a central hub or switch. Data travels from one device to another through the hub or switch. 4. Mesh topology. In a mesh topology, every device is connected to every other device. This provides redundancy and ensures that data can be sent even if one or more devices fail. Implementation. Networks can be implemented using various technologies and protocols. Ethernet is a popular technology for LANs, while WANs often use technologies like MPLS or VPNs. Network protocols like TCP/IP are used to ensure that data is transmitted reliably and efficiently across the network. In addition, network security measures such as firewalls and encryption are important for protecting the network and its data from unauthorized access. 11. Algorithm properties. Structured algorithm design. Depiction of algorithms using planar structograms. Algorithm properties are characteristics of algorithms that are used to evaluate their effectiveness and suitability for specific tasks. Some of the key properties of algorithms include correctness, efficiency, simplicity, and generality. Correctness: an algorithm is considered correct if it produces the expected output for all possible inputs. This property is crucial because if an algorithm produces incorrect output, it is not useful for solving the problem it was designed for. Efficiency: an efficient algorithm is one that uses the minimum amount of time and resources necessary to solve a problem. Efficiency is measured in terms of the algorithm's time complexity and space complexity. Simplicity: a simple algorithm is easy to understand and implement. It is important to keep algorithms simple so that they are maintainable and can be modified easily when needed. Generality: a general algorithm is applicable to a wide range of problems. A general algorithm is more useful than a specific algorithm because it can be used in a variety of contexts. Structured algorithm design is a method of designing algorithms using a set of standardized techniques and conventions. The goal of structured design is to create algorithms that are easy to read, understand, and modify. Structured design involves breaking down the problem into smaller, manageable subproblems, and then designing algorithms to solve each subproblem. Planar structograms are a type of diagram used to represent algorithms in structured design. Planar structograms use a set of symbols and conventions to depict the flow of control and data through the algorithm. This allows developers to visualize the algorithm and identify potential issues or improvements. Planar structograms are an effective way to communicate the design of an algorithm to other developers and stakeholders. 12 Flow control structures. If/else/else if conditional statements. Branching program flow using the switch statement. While and do-while loop statements. Flow control structures are programming constructs that allow the execution of a program to be controlled based on certain conditions or loops. These structures are essential for building complex programs that can handle a variety of inputs and conditions. Conditional statements, such as if/else/else if, are a type of flow control structure that allows a program to execute certain code blocks only if certain conditions are met. The if statement evaluates a condition, and if it is true, the code block following the if statement is executed. If the condition is false, the code block is skipped. The else statement provides an alternative code block to execute if the if condition is false. The else if statement allows for additional conditions to be checked if the previous if or else if condition is false. Switch statements provide another type of flow control structure that allows for branching program flow based on the value of a variable or expression. The switch statement evaluates a variable or expression and compares it to a list of case values. If the variable or expression matches a case value, the code block associated with that case is executed. If there is no match, the default code block is executed. Loop statements, such as while and do-while, allow for repeated execution of a code block until a certain condition is met. The while loop evaluates a condition before executing the code block, and continues to execute the code block as long as the condition is true. The do-while loop is similar to the while loop, but it evaluates the condition after the code block has been executed at least once. In summary, flow control structures such as if/else/else if, switch statements, and while/do-while loops are fundamental programming constructs that allow for the execution of a program to be controlled based on certain conditions or loops. By utilizing these structures, programmers can create more complex and flexible programs that can handle a variety of inputs and conditions. 13 Modular programming. Functions and function parameters. Return value of a function. Recursion. Variables and their memory representation. Pointers. Modular programming is a software design technique where a program is divided into smaller and independent modules, each responsible for a specific task or functionality. This approach makes it easier to understand, develop, and maintain large software systems by breaking them down into smaller, more manageable parts. Functions are a fundamental part of modular programming. They are self-contained blocks of code that perform a specific task. Functions can be called from other parts of the program and can take inputs in the form of function parameters. Function parameters are variables that are passed to the function when it is called, allowing the function to use or modify them as needed. The return value of a function is the result of its computation. When a function is called, it can return a value back to the calling code, which can then use that value for further processing or display. The return type of a function specifies the type of value that it will return. Recursion is a programming technique where a function calls itself to solve a problem. This technique is useful for solving problems that can be broken down into smaller, similar subproblems. Recursion is often used in algorithms that traverse data structures such as trees and graphs. Variables are used to store data in a program. They have a name, a type, and a value. The memory representation of a variable depends on its type. For example, integer variables are stored as binary numbers in memory, while string variables are stored as a sequence of characters. Pointers are variables that store the memory address of another variable. They allow programs to access and manipulate memory directly, making them a powerful tool for low-level programming tasks. Pointers are commonly used in dynamic memory allocation, where a program allocates memory for variables at runtime. 14. Prepositional logic. Preposition. Logic variable. Logic conjunctives and examples of their use. Logic formulas. Propositional logic, also known as propositional calculus, is a branch of mathematical logic that deals with propositions or statements, and how they are related to each other through logical operations. In the context of system information and computer engineering, propositional logic is used to design and analyze digital circuits, develop programming languages, and reason about the correctness of computer programs. Propositions or statements are sentences that can be either true or false. For example, the sky is blue is a proposition that can be either true or false depending on the current state of the sky. Propositions are usually denoted by letters such as P, Q, R, etc., and are called logic variables. Logical connectives, also known as propositional connectives, are symbols that connect propositions to form compound propositions. The most common logical connectives are negation, conjunction, disjunction, implication, and equivalence. Negation: the negation of a proposition P is denoted by P and is true if P is false, and false if P is true. For example, if P is the sky is blue, then P is the sky is not blue. Conjunction: the conjunction of two propositions P and Q is denoted by PQ and is true only if both P and Q are true. For example, if P is the sky is blue and Q is the sun is shining, then PQ is the sky is blue and the sun is shining. Disjunction: the disjunction of two propositions P and Q is denoted by PQ and is true if at least one of P and Q is true. For example, if P is the sky is blue and Q is it is raining, then PQ is either the sky is blue or it is raining. Implication: the implication of two propositions P and Q is denoted by PQ and is true if P implies Q. In other words, if P is true, then Q must also be true. If P is false, then the implication is true regardless of the truth value of Q. For example, if P is if it rains, the ground gets wet and Q is the ground is wet, then PQ is if it rains, the ground gets wet, therefore the ground is wet. Equivalence: the equivalence of two propositions P and Q is denoted by PQ and is true if and only if P and Q have the same truth value. For example, if P is the sky is blue and Q is the grass is green, then PQ is false. A logic formula is a compound proposition formed by applying one or more logical connectives to one or more logic variables. For example, PQ, R is a logic formula that says if P is true and Q is true, then R must be false. In summary, propositional logic provides a systematic way of reasoning about propositions, and how they are related to each other through logical operations. It is an essential tool for computer engineers to design and analyze digital circuits, develop programming languages, and reason about the correctness of computer programs. 15 Static and dynamic data structures. Queue, stack, linked list, tree. Static and dynamic data structures refer to how the data is organized and stored in a computer's memory. Static data structures are predefined and have a fixed size, meaning their size does not change during program execution. Arrays are a common example of a static data structure. Once an array is declared, its size cannot be modified. Static data structures are suitable for storing fixed amounts of data, but they can be limited in terms of flexibility and efficiency. Dynamic data structures, on the other hand, can be resized during program execution to accommodate changing amounts of data. They use pointers to reference memory locations and allow for efficient allocation and deallocation of memory. Some examples of dynamic data structures include linked lists, trees, queues, and stacks. A queue is a dynamic data structure that follows the first-in first-out (FIFO) principle. It operates like a queue of customers waiting in line to be served. The first customer who enters the queue is the first to be served. A stack is a dynamic data structure that follows the last-in first-out (LIFO) principle. It operates like a stack of plates. The last plate that is placed on the stack is the first to be removed. A linked list is a dynamic data structure that consists of a sequence of nodes, where each node contains data and a reference to the next node in the sequence. Linked lists are useful for situations where the size of the data is unknown or can vary. A tree is a dynamic data structure that consists of nodes arranged in a hierarchical structure. The top node is called the root, and each node can have one or more child nodes. Trees are useful for representing relationships between data, such as family trees or organizational structures. Each of these dynamic data structures has its own unique properties and use cases, and the choice of which one to use depends on the specific requirements of the program or system being developed. 16. Relational data model, relational algebra, relational database terminology, CODS rules. Relational data model. The relational data model is a way of representing data in a structured manner. It is based on the idea of organizing data into tables, where each table represents a single entity or concept and each row in the table represents a specific instance of that entity. The columns in the table represent attributes of the entity, such as its name, age, or address. Relational algebra. Relational algebra is a mathematical language used to manipulate data in relational databases. It consists of a set of operations that can be applied to tables, such as selection, projection, join, and union. These operations allow users to perform complex queries on the data, extracting only the information they need. Relational database terminology. There are several terms used in the context of relational databases that are important to understand. Here are a few of the most common: table, a collection of data organized into rows and columns. Row, a single record in a table that represents a specific instance of an entity. Column, a single attribute of an entity that is represented in a table. Primary key, a column or set of columns in a table that uniquely identifies each row in the table. Foreign key, a column in one table that refers to the primary key of another table. Index, a data structure that provides fast access to specific rows in a table based on the values in one or more columns. CODS rules. CODS rules are a set of guidelines for designing and implementing relational databases. They were developed by E.F. Codd, the inventor of the relational data model, in the 1970s. There are 12 rules in total, but here are a few of the most important. Rule 1, Information Rule: all information in the database must be represented in tables. Rule 2, Guaranteed Access Rule: each piece of data in a database must be accessible via a combination of table name, primary key value, and column name. Rule 3, Systematic Treatment of Null Values: the database must support the representation of missing or unknown data. Rule 4, Dynamic Online Catalog: based on the relational model, the structure of the database, i.e. the tables, columns, and relationships, must be stored in the database itself. Rule 5, Comprehensive Data Sublanguage Rule. The database must support a language for querying and manipulating the data that is based on relational algebra. 17 Data Integrity Types of Integrity Constraints, Database Triggers. Data Normalization, Data Redundancy, Normal Forms. Data Integrity. Data integrity refers to the accuracy and consistency of data over its entire life cycle. This means that the data must be reliable, consistent, and free from errors, duplications, or inconsistencies. Types of integrity constraints. Integrity constraints are rules that ensure the validity and accuracy of data stored in a database. There are 4 types of integrity constraints. A. Entity integrity. This constraint ensures that each row in a table has a unique identifier, known as the primary key. B. Referential integrity. This constraint ensures that the relationships between tables are maintained by enforcing the foreign key constraints. C. Domain integrity. This constraint ensures that the data entered into a column is of the correct data type and within the permissible range. D. User-defined integrity. This constraint allows you to create custom rules to ensure data integrity. Database triggers. Triggers are special types of stored procedures that are automatically executed in response to certain events, such as inserts, updates, or deletes, occurring in a database. These triggers can be used to enforce business rules, validate data, or perform other actions. Data normalization. Data normalization is the process of organizing data in a database to reduce redundancy and dependency. The goal is to minimize data redundancy and ensure that each piece of data is stored in only one place. Data redundancy. Data redundancy refers to the storage of the same data in multiple places in a database. This can lead to inconsistencies, errors, and data loss if not managed properly. Normal forms. Normal forms are a set of guidelines for designing a database that adheres to data normalization principles. There are several normal forms, including first normal form, 1NF, second normal form, 2NF, third normal form, 3NF, and so on. Each normal form builds upon the previous one and has stricter requirements for data normalization. The ultimate goal of normal forms is to reduce data redundancy, improve data integrity, and ensure efficient database performance. 18 Database transactions, purpose and principles, implementations. Database transactions are a fundamental concept in computer engineering that helps ensure the reliability and consistency of data stored in a database. A database transaction is a sequence of operations performed on a database that are treated as a single unit of work, meaning that either all the operations are executed successfully, or none of them are executed at all. The purpose of a database transaction is to ensure the integrity and consistency of data by enforcing the principles of atomicity, consistency, isolation, and durability, ACID. The ACID principles ensure that a transaction is executed in a way that guarantees that the data is always in a valid state, regardless of any errors or concurrent operations that may occur. The ACID principles can be explained as follows. Atomicity. A transaction is atomic, meaning that it is treated as a single unit of work. Either all the operations in the transaction are executed successfully, or none of them are executed at all. This ensures that the database remains in a consistent state. Consistency. A transaction should ensure that the database remains in a consistent state. This means that any changes made by the transaction should not violate any of the constraints or rules that govern the database. Isolation. A transaction should be executed in isolation from other concurrent transactions. This means that the changes made by one transaction should not be visible to other transactions until the first transaction has been completed. Durability. Once a transaction has been committed, the changes made by the transaction should be permanent and should survive any subsequent failures or crashes. Implementing database transactions involves using transaction management protocols that allow applications to manage the flow of transactions and ensure the ACID principles are upheld. Some of the most common implementations include two-phase commit. a protocol that ensures that all nodes involved in a transaction are in agreement before committing the changes. Optimistic concurrency control, a protocol that allows multiple transactions to access the same data simultaneously, but only commits the changes if there are no conflicts. Pessimistic concurrency control, a protocol that locks the data being accessed by a transaction, preventing other transactions from accessing it until the first transaction has completed. Overall, the use of database transactions is a critical aspect of ensuring the integrity and consistency of data in a database, and understanding the principles and implementations involved is essential for computer engineers and anyone working with databases. 19 Query languages, purpose and principles, SQL and QBE, SQL Standard, SQL Critique. Query languages are used to retrieve and manipulate data in a database. There are two main types of query languages, procedural and non-procedural. Procedural languages require the user to specify how to perform a task, while non-procedural languages allow the user to specify what task to perform and the system figures out how to do it. SQL and QBE are examples of non-procedural query languages. The purpose of query languages is to provide a way for users to interact with a database without having to understand how the data is stored or organized. Query languages provide a standardized way to access and manipulate data, making it easier for developers to create applications that interact with databases. The principles of query languages include the ability to retrieve data based on specific criteria, the ability to update or modify data in the database, and the ability to join data from multiple tables. These principles allow users to retrieve the exact data they need, modify it as necessary, and combine data from different tables to create more complex queries. SQL, Structured Query Language, is a standard query language used for managing relational databases. It is a popular language for managing data in large organizations and is supported by a variety of database management systems, DBMS. SQL allows users to retrieve data based on specific criteria, insert new data, update existing data, and delete data from a database. It also supports complex queries, such as joining data from multiple tables and grouping data by specific criteria. QBE, Query by Example, is another non-procedural query language used for managing databases. It allows users to retrieve data by specifying an example of the data they are looking for, rather than writing complex SQL queries. QBE is often used by users who are less familiar with SQL or who need to quickly retrieve data without having to write a lot of code. The SQL Standard is a set of guidelines that dictate how SQL should be implemented by database management systems. The SQL Standard is maintained by the International Organization for Standardization, ISO, and the American National Standards Institute, ANSI. The SQL Standard ensures that SQL is implemented consistently across different DBMSs, making it easier for developers to write applications that work with multiple database systems. SQL has been criticized for being difficult to learn and for having a steep learning curve. Additionally, some experts argue that SQL is not flexible enough to handle certain types of data, such as unstructured or semi-structured data. However, SQL remains one of the most widely used query languages and is an important skill for anyone working in system information and computer engineering. 20 Relational and object databases, data storage, data access, data security. Relational databases and object databases are two different approaches to organizing and storing data. Relational databases store data in tables, which consist of rows and columns. The relationships between different tables are defined by keys, which allow data to be easily accessed and manipulated. Relational databases are widely used in applications such as accounting, inventory management, and customer relationship management. Object databases, on the other hand, store data as objects. These objects can contain data, as well as methods for manipulating that data. Object databases are often used in applications such as e-commerce, social media, and gaming. Data storage refers to the physical storage of data on computer systems. This can include hard drives, solid-state drives, and other types of storage media. Different types of storage media have different performance characteristics, and the choice of storage media can affect the performance of a system. Data access refers to the process of retrieving and manipulating data stored in a database. This can involve writing queries to search for specific data, performing calculations on data, and updating or deleting data. Different databases have different ways of accessing and manipulating data, and the choice of database can affect the performance and functionality of a system. Data security is an important consideration in any computer system that stores and manipulates data. This can include measures such as encryption, authentication, and access controls. Encryption can be used to protect data as it is transmitted over networks or stored on physical media. Authentication can be used to ensure that only authorized users have access to data, and access controls can be used to limit the actions that users can perform on data. Data security is particularly important in systems that store sensitive information, such as financial data or personal information.